Hello everyone, welcome back to Networks class. Last time what we did was we went over some of the answers to homework 1, and then at the end of class we talked about unimodular constraint matrices. So unimodularity was this property about how every basis matrix had a determinant of either +1 or -1, and really it was that property that let us drop these integer constraints that we had for a shortest path problem and to just make them the variables be positive and know for a fact that all the extreme points still have just 0 or 1 coordinates exactly like we wanted. Um, so that's what we did last time. And the plan for today is to do a bit of an overview of the different kinds of network models that we're going to study in class. So the reason that we're doing this overview is because very soon for your projects, I'll be asking you to try to figure out what kind of network model applies for your particular real world situation. So today is just going to be a bit of a survey. And really, we're going to spend the rest of the quarter looking at each of these models in detail to try to understand it better. So this is just a very high level view for today. So in terms of network models, there's really four basic kinds of network models that we're going to study in class. And you're already familiar with one of them. So this one we've studied for a while. That's the shortest path problem. And the basic idea behind the shortest path problem is that we have some data. The data that we have is that for each edge, we have kind of a length of edge ij. But these lengths could mean lots of things, right? So they don't have to be in terms of kilometers or miles or something like that. They could be in terms of time, or they could be in terms of fuel, or you'll see very soon in the homework assignment, these lengths could also be a measure of safety. So it could be kind of like the probability that you actually are able to make it through this edge without getting attacked or something like that. And really, that's the basic data for the problem. And then the goal of the problem is to find the shortest path from some node S to T. And the way that we modeled this was with a linear program that looked like this. So minimize over y, the sum of the Cij, Yij's. So this is the total cost of the path. And then we had some constraints. So the constraints look like this. So this is the trucks going into S, the trucks going out of S, the trucks going into T, the trucks going out of T, and then all the other nodes. And then we had that the Yij's have to be positive. So that's the very basic shortest path problem. And we've already seen in class that it's applicable to various real world situations. But one kind of common twist to this problem that I want to point out is the following, that oftentimes what we want is something like the shortest path, but in addition to wanting the shortest path, we might have some kind of fuel usage. So suppose it takes Fij units of fuel to move across edge ij. And that suppose also we have a total fuel budget of B. So how can we say that we want the shortest path, but subject to not using too much of our fuel? Well, the way to do this is to just add a constraint that says don't use over your fuel budget. So the total amount of fuel that we would use is something like this, because the Yij variables are 1 on the path that we use and 0 otherwise. And so when we multiply it by the Fij's, this gives us the total fuel. on the path that we've chosen, and we want that to be less than or equal to b. So you can add a constraint like this to the above linear program, and it'll try to find shortest path subject to this fuel constraint. But one thing I want to point out, and we'll talk about this more in detail later in the quarter, but as soon as we add this extra constraint into the shortest path problem, it immediately breaks the nice unimodularity properties that we saw in class last time, because now each column of the constraint matrix doesn't have just 1, plus, and minus 1. There's these Fij's also. And so what happens is that the answers that you get out might not be just zeros or ones. But it's okay because the Yij's have a very natural interpretation in this case. And the interpretation is the following, that the solution is basically going to randomize between a couple of paths. So one path might be using too much fuel and another path might be using slightly less than B fuel. But in expectation, it's definitely going to satisfy this fuel constraint. So this constraint that we're adding here, you can think of it as kind of a in expectation constraint. So if you repeat this many times, don't use more than B fuel. So so this is the first basic network model that we'll study in class. And here we had just one truck moving from S to T. So let's start with this and try to think about creating some of the other models that we're going to see in class. So for this next problem, or for the original shortest path problem, we had just one truck leaving S and one truck entering T. But suppose that we wanted to have 5 trucks leaving S and 5 trucks entering T. The way we would do that is just change these 1s to 5s, right? So now there's 5 trucks leaving S and 5 trucks entering T, and no trucks are stopping or getting created anywhere else. So now suppose that we had the following problem. So suppose that instead of having costs on the arcs, we have a capacity for every arc. So in other words, we have this number Uij, and it tells us that no more than Uij trucks can go through this particular arc. So somebody comes along and gives us these capacities. You can think of them as now every arc is perhaps a pipeline, and Uij says how much material we can move down this pipeline. And our goal is to find the maximum number of the maximum amount of supplies we can move from S to T. Okay, so clearly, since our goal is to find the maximum amount of supplies, if we try to create this or write this problem down as a linear program, the objective function wouldn't be the one that we had earlier. It would be something that's a maximum. And we don't know how many trucks we want to move from S to T. So this right-hand side is going to be some kind of variable. So we're going to still have the y variables that tell us how many trucks we put on each arc. But in addition to the y variables, we're going to have this v variable that tells us the total amount of material, moved from S to T. So if V represents the total material moved from S to T, then what we want to do is maximize V. And the right-hand sides of these two equations are simply going to be minus V, because V trucks are going to be leaving S, and plus V because V trucks are going to be entering T. So now this right-hand side is a variable, and we're trying to get that as big as possible. So this is the second kind of network modeling problem that we're going to talk about in class. And this is called the maximum flow problem. And very typical kinds of applications for a maximum flow problem are things like an oil pipeline or a gas pipeline. So how much oil can this pipeline move? And if somebody comes along and takes out a particular part of the pipeline, how much does that impair the pipeline's capability of moving material now? Um, so that's kind of a stereotypical example you can think about in terms of max flow. So that's the second problem that we'll discuss in class. The third problem has the following kinds of data. And before we get into this problem, you can kind of motivated by thinking about the maximum flow problem. There's something kind of unsatisfying about maximum flow because we're trying to move as many trucks from S to T, but there isn't a cost of moving a truck one way versus moving a truck another way. So that's what the next problem is going to try to take care of. So the way you can think about this problem is as follows. So suppose here we have a graph and we have some supply points. So this is maybe a supply point over here, a supply point over here. And we have some demand points. So maybe here's 3 demand points. A demand here, a demand here, and a demand here. And our goal is to basically move all of these supplies to their demands. So you can think of this as I have 5 crates of material here, and over here they need maybe 3 crates, and over here they need 2 crates. And so I have to figure out a trucking plan to move all of this material from its supplies to its demands. So here's the basic data that we would have for this problem. So the data would be something like this. Cij would be the cost of moving one unit of goods across edge ij. Uij would be the capacity of edge ij. So this is same as in maximum flow. Maybe some particular edges only take 5 trucks and no more can pass through there. But in addition to these two, we also have something that we'll call B of A, which is going to be the supply or demand of material on node A. So in particular, supplies are going to be negative. Demands are going to be positive. And every other node that's neither has a supply nor demand is just a node where things are moving through. And so this is going to be just 0 for transshipment nodes. So these are the nodes that neither have supply nor demand. They're just kind of in between. So the goal for this problem is going to be to satisfy the demands given the supplies. So we have to move all of the supplies to the various demand locations where those supplies are required. And we want to do this at minimum cost. So let's try to write a linear program for this. So we want to do this at minimum cost. So here we're going to minimize. And the cost is going to look very similar to the one for shortest path. So Yij, again, is the number of trucks that are going on arc ij. And Cij is the cost per truck. So over here is just the total cost of our shipping plan. And let's write down the constraints for this to see what they look like. So here we have a node A, and we have all the trucks going into A minus all the trucks going out of A. And that's going to be equal to, we're going to set this right-hand side equal to this supply or demand parameter, the B of A. So let's see why this makes sense. So a supply node is going to have more trucks leaving it than entering, because those trucks leaving it are going to be taking the supplies out of there. So this right-hand side is negative for a supply, which exactly says more trucks are leaving a supply node than entering. It's going to be positive for a demand, which means that more trucks are entering a demand node than are leaving it. And you don't necessarily have to think of this as trucks. You can think of this as crates. So more crates are leaving a supply node than are entering. More crates are entering a demand node than are leaving. And this is 0 for everything else. And that's because all of the other nodes that have neither a supply or demand, whatever crates came into the node have to go out of the node. And so that's why the B of A's have this property of being negative, positive, and 0 for everything in between. So in addition to having these constraints for the trucks that are going in and out of a node, we have to have some constraints that satisfy these capacities. So we have to say something like no more than so many trucks can use this edge. And we can just do that with constraints like this. The yij's have to be less than or equal to the uij's, and the yij's have to be bigger than or equal to 0. So this problem of moving supplies to various demand locations at minimum cost is called the minimum cost flow problem. And so just based on this discussion, you should already see that there's a strong relationship between shortest path and the minimum cost flow problem. So in particular, if we go back and look at shortest path, you can see that there was just 1 minus 1 here, 1 plus 1. So you can think of this shortest path problem as just a minimum cost flow problem where there's just one crate that has one supply on S. There's one unit of demand on T, so T wants one crate. And we didn't have any capacities on the edges, so the crate can move over any edge that we want. But in this more general version, we can have multiple supplies of crates on various nodes, and the supply could be on more than just one node. We can have more than just one location of demand, and in addition, we have some capacities here on the edges that tell us you can't move more than so many trucks through here. So there's a lot of kind of details to these problems that in this brief overview, we don't have that much time to go into, but here's just kind of some preview of that. So first, let's think about these B of A's and all of them. So imagine that the total demand was 7 crates, and I only had 5 crates of supply in total. Well, if that were the case, then this linear program is going to become infeasible. And that's because you want more crates to be going into nodes than there are crates that are getting created at other nodes. And so really the sum of these B of A's for this program as we've written it to work out have to be equal to 0. But there is something you can do if the demands and the supplies don't happen to be aligned, don't happen to be equal to each other. And that's you can add some auxiliary variables here. So you can do something like plus unsatisfied demand. So if you do something like this, these unsatisfied demand variables make sure that everything is balanced. And even if the demand and the supply don't exactly meet each other, then still the problem is feasible. So that's one kind of common twist on this problem. But another common twist actually to this problem and the previous problem is that we might have some lower bounds. So may have something like a Lij, which is going to be a lower bound on edge ij. So this says something like you have to have at least this many trucks going through this edge. And you can think of this as maybe a contractual obligation or something like that. And the way we can incorporate this into this problem is just by adding constraints like this, that Lij, Lij has to be less than or equal to Yij. So in this way, we make sure that the number of trucks going across the edge has to be at least the amount that we required. So that's the third basic kind of network problem that we'll look at in class, this minimum cost flow problem. So let's look at the fourth problem. And to do this, let's again just motivate it with a picture. So suppose now that over here I have a supply of, let's say, corn. And over here I have a demand for corn. Over here we have a supply for rice. And over here we have a demand for rice. Now, in the minimum cost flow problem, when we had supplies and demands, we didn't care which demand was satisfied from which supply. So maybe this demand gets satisfied from here, maybe this demand gets satisfied from here, this one from here. Whichever way it is, it's really the optimization problem that gets to decide which supply goes to which demand, and it's going to do it in a way that minimizes the total cost. But for a multi-commodity flow problem, or for this next problem that we're going to look at, we want to make sure that the demand for corn gets actually satisfied from a supply for corn. So we don't want to somehow bring rice trucks into this demand for corn and call the demand satisfied, because really that's a demand specifically for corn and not for rice. And in addition to kind of making sure that each kind of demand gets satisfied by the appropriate kind of supply, we might have lots of additional kinds of data. So these two kinds of commodities, corn and rice, might have totally different costs. So Cijk might be the cost for moving commodity K across edge ij. So this might be totally different for rice than corn, because maybe rice trucks are much more expensive than corn trucks. We also might have some kind of capacity. So Uijk is the capacity for trucks of commodity K across edge ij. So the way to think about this is that you might have some edge that allows only one rice truck to go through, but maybe it allows up to 4 corn trucks. Or another way you can think of it is that maybe in the middle of this graph here, we have some country that is perfectly fine allowing corn through, but they don't want to allow rice through. So for all of these edges inside of here, the capacity for rice is 0, but the capacity for corn is maybe bigger than 0. So that's why we have possibly a different capacity for each kind of commodity. In addition, we have a different supply and demand for each kind of commodity. So this is the supply or demand of commodity K on node A. So some nodes, for example, this node has a supply of rice, say, but no supply of corn. Or we could have a node that has both a supply of rice and a supply of corn. But either way, for each node and each commodity, this tells us how much supply demand of each there is. And of course, these B's are 0 for nodes that have neither a supply of rice nor a supply of corn, nor a demand, nor for each of these products. So you might imagine, let's take a look at this node. It has a supply for rice. So its supply for rice is going to be negative. But in terms of corn, it has neither supply nor demand, but it could still be a transshipment point for corn. So its B for corn is going to be just 0. So let's try to write down what this problem looks like of trying to satisfy all these demands from the given supplies. So clearly we're going to want to minimize costs here. So we're going to minimize over some y variables. And the cost is going to be the sum over all demands or all different commodity types, because we have to move the corn and we have to move the rice. So this is the sum over commodity types. And then we're going to sum over edges ij. And here we have the cost of moving commodity k across edge ij. But now we have to multiply it by the number of trucks that are crossing this edge. And writing down yij just simply isn't enough, because yij before determined just the number of trucks crossing the edge. But now we really want to keep our rice trucks separate from our corn trucks, because we want to keep track of what kind of material this truck is actually transporting. So that's why we're going to have yijk. This is the number of trucks carrying commodity k that cross edge ij. So since those trucks are carrying exactly commodity k, that's why we're multiplying them by this cost to get the total cost of moving commodity k. And we're summing that over all the commodities. Okay, so now let's write down the constraints. So here we're summing in all the trucks, all the rice trucks that are entering node A. We're subtracting all the rice trucks that are leaving node A. And that has to be equal to whatever the supply or demand for rice was at that node. So this is for all nodes A and commodities K. So these equations here just keep all of the trucks for the different commodities separate from each other. So we're doing one set of accounting for the rice trucks and another set of accounting for the corn trucks. We can incorporate these capacity constraints like this. So the number of trucks, the number of rice trucks crossing edge ij can't be more than the number that's allowed for that particular commodity. So this is for all edges ij and commodities k. And of course we want the number of trucks of each type crossing each edge to be bigger than or equal to 0. So in addition to this, one of the things that often happens is we have another piece of data, which is a capacity for the, so this is a capacity on the total number of trucks that cross edge ij. So this is different than the original ones because this is per commodity. So just to give you an example of this, imagine that we have two nodes here, I and j. And across this edge, maybe we're allowed to use 4 corn trucks, no more than 4 corn trucks, no more than 5 rice trucks, but maybe in total you can have no more than 7 total. So regardless of how you allocate between your corn and rice, you have to make sure that no more than 7 trucks total are crossing this edge. So the way you can incorporate constraints like that is to write something like this. So we have to count the total number of trucks going across the edge. So that means we have to sum over all the commodities, the number of trucks of that commodity that are crossing the edge, and that has to be less than or equal to this capacity. So the left-hand side here is the total number of trucks crossing the edge, and the right-hand side is that capacity. So this is the fourth general kind of network problem that we're going to look at in class, and it's called the multi-commodity flow problem. And it's called multi-commodity flow because, of course, we have many different commodities, and we want to make sure that we're shipping each kind of commodity. So the last kind of network problem that we'll talk about isn't a model that's kind of a model on itself. Like you can think of it as kind of a hybrid model between lots of different other network models. So just to kind of give you an example is, so suppose we're solving shortest path. But we don't know the start and end points. So you can imagine that maybe sometimes I might be driving to work, sometimes I might be driving to the grocery store, sometimes I might be driving to the hospital, and I don't know exactly what the starting or the ending point of a path is. But I have a few kind of scenarios. So you can think of a scenario as kind of describing, these describe all the uncertain pieces of data. So in terms of this start and destination point, you can think of having maybe one scenario that goes from S1 to T1, and another scenario that goes from S2 to T2. So these are totally different nodes. And maybe when I go from S1 to T1, I might have other pieces of uncertainty. For example, it might be high traffic. And if it's high traffic, maybe some edges of the network aren't available. Or maybe it's low traffic in this scenario. And if it's low traffic, maybe more edges are available for me. Or maybe if it's high or low traffic, what this is doing is editing the costs. Because maybe on high traffic, it takes me a lot longer to traverse some edge than it would during low traffic. So each scenario completely describes one possibility for the uncertain pieces of data. And with each scenario, we have a probability. So with each scenario, we have a probability. So for this example, maybe this scenario is 2/3 likely and this scenario is 1/3 likely. So we'd like to evaluate how well our network performs under these various scenarios. With each scenario, we have a probability, and we're going to use these probabilities to basically create an expected network problem. So let me just show you an example and then we can discuss. So the idea here is that we're going to minimize over some y variables. And over here, I maybe have the costs under scenario 1. And these y variables kind of describe the shortest path I would take under this first scenario. And on the other side, I have an entirely different set of y variables, which tell me the shortest path I would take under the second scenario. And in this objective function, I'm just literally going to weight these by their probabilities. And the constraints are just going to be totally separate for these two. So here I have everything that's going into S1 minus everything that's going out of S1. Everything for T1. Everything for these intermediate points. So this just describes the shortest path problem for the first scenario. And on the other side, I'm going to describe just the shortest path problem for the second scenario. So these two right now, you can think of them as just totally separate network problems. But the objective function here is kind of a weighted sum between the objective functions of these two separate problems. So to give you an example of how one might use this in real-world modeling, suppose that we're trying to figure out fire department's expected response time to a fire. But I don't know where the fire might be. So I might have a bunch of scenarios of possibilities of where the fire could be. And I could have a probability distribution over these scenarios. So for example, I think it's very likely that there might be a fire at the airport, slightly less likely that there would be one at the hospital, maybe equally likely as that to be one at NPS, etc. And then here we have a shortest path problem that describes the fire department's response time to each of these. So this would be the fire department's response time to the airport. This would be the fire department's response time to the hospital. And what the objective function is doing is literally computing the expected response time of the fire department, where the expectation is taken over all of the possible scenarios. And in this example here, we just did two shortest path problems, but you could really mix and match any of the network models that we talked about in class. So for example, maybe you're evacuating some people, which maybe you're modeling as a max flow problem, but at the same time that you're evacuating people, you need to move in an ambulance, and that's some kind of shortest path problem. And so here you might have one thing that's a max flow and another thing that's maybe a shortest path for that particular problem. And in general, this kind of model is called a stochastic network model. And one thing I want to point out about the stochastic network model is that in some sense it's different than these four other ones that we've seen, but it's actually very, very similar to this multi-commodity flow, because in multi-commodity flow, our different scenarios here are just kind of the different commodities. And in the objective function here, we've just summed all of these together. But we're kind of summing them with weights of 1. But maybe the cost for rice to us is much more important than the cost for corn. And then you could potentially put different weighting factors here in the objective function. And so the only kind of basic difference is that for the stochastic one, here I said that these two are totally separate network flow problems. But in the multi-commodity flow, you saw that we had this one constraint here that kind of mixes the different things. So this is a constraint that mixes one commodity with another. And you could similarly have things over here. If your particular application needs it, maybe you have some constraint that involves the y variables from one scenario and the y variables from another scenario. But you'd have to be careful to actually think about exactly what that means in your particular situation for your particular real world model. So those are the basic tools that we're going to talk about for the rest of class. And we're going to go into each of these in detail and look at lots of real world situations where they're applicable. But for right now, I wanted you to get this overview of the different models because very soon I'll be asking you to think about your projects and to try to figure out which one of these models or is most applicable to the particular real world situation that you're thinking about modeling. So that concludes lecture for today. Thanks a lot for listening, and I'll see you all next time.